Okay, so today we're going to study about oscillations. Now, you see why the study of what is oscillations and why the study of oscillation is very important for a student of engineering. You see, our world is filled with oscillations, in which what happened, in which in oscillations, object moves back and forth repeatedly. Okay, so when something moves back and forth repeatedly, we call it oscillations. And among these oscillations, many oscillations are merely amusing, and some are annoying as well. Okay, like amusing is when you are listening music, so it gives an amusement to you, and when a baby is crying, okay, so you do not like it, so that is an annoying. Okay, but many others are dangerous. So some of the oscillations are dangerous. The examples of dangerous oscillations is earthquake. Okay, okay, we're gonna discuss this thing later on over here. And some of the oscillations are financially important. Okay, now examples of the oscillations: when a bat, the baseball, although it is not in popular in Bangladesh, but the baseball player, when he hits the ball, okay, when a bat hits a baseball, the bat may oscillate enough to sting the batter's hand or even break apart. Okay, so sometimes it can be dangerous as well. When wind blows past a power line, overhead power line, the line may oscillate so severely that it rips apart and shutting off the power supply to a community. And there is what the dangerous one: when an earthquake occurs near a city, building may set oscillating so severely that they are shaken apart. So it's dangerous oscillations. And all this one is not available in our country. So sometimes you can buy something from coin box, the vending machine, which is called. When a coin drops into a metal collection plate, okay, the coin oscillates with such a familiar ring that the coin's denomination can be determined from the sound. Okay, so machine can understand by noting the oscillations. It can understand what is the what amount of coin you drop in the metal collection plate. Okay, so therefore, from the above discussion, the study and control of oscillations are two of the primary goals of both physics and engineering. So that is why the study of oscillations is important for student of physics and also engineering. Okay, so among these oscillations, simple harmonic motion is one type of oscillations. So in this figure, you can see the sequence of snapshot of simple oscillating system. A particle moving repeatedly back and forth about the origin of an x-axis. That's the origin. One important property of the so the particle is moving and then it's coming back again and then again and so on. Okay, so one important property of the oscillatory motion is its frequency or number of oscillations that are completed each second, and that is called frequency. Okay, and that is denoted by F, and the SI unit of frequency is actually hertz. That is in honor of Henry, German physicist Henry Hertz. We call it hertz, Hz, where 1 hertz is denoted by 1 Hz, and that is 1 oscillation per second. Okay. So in this case, what happens when the particle try to moves from here? You see the velocity in this figure. I show the velocity of the particle when it is oscillating. So when it starts from here, its velocity is 0. So it has got the potential energy, okay? And that potential energy converted to kinetic energy. That means it has got velocity. And the velocity is maximum when it is passing through the origin. Velocity is maximum here. And then again, so that means in this case, it has fully potential energy, kinetic energy is 0. When it arrives here, all potential energy converted to kinetic energy. So potential energy is 0 here. That is why it moves, and then kinetic energy converted to potential energy. That means its velocity decreases. When it comes here, all the kinetic energy converted to potential energy, and then it start to move again in the backward direction. Okay, again when it passes through the origin, its velocity is maximum. Again, its velocity is 0 here. That means it acquired potential energy, and utilizing this potential energy, it moves back and forth again. Okay, so when it suppose this is the 0 in your clock, when it arrives here, the time required is actually 1/4 of the period. So this is t/4. And here, when it arrives here, it is actually half of the period, 3/4 of the period, and here it completes the full oscillations. So time required to move from here, going there and coming back again here, we call it one complete oscillation. And time required to complete one oscillation, we call it time period. And 1/1 time period is called the frequency of the particle. Okay. So related to the frequency that I have already mentioned, T equal to 1/f or f equal to 1/t. Okay. So that means any motion that repeats itself at a regular interval is called periodic motion or harmonic motion. So the motion in figure 1a that I have shown earlier, for such motion, the displacement x of the particle from the origin is given by a function of time. As you can see, this one is a function of time. So we can represent this one by using displacement is a function it depends on time, and that is xm. Xm is the maximum amplitude, and then maximum displacement, which is called amplitude. Xm cos of omega t plus phi, in which xm, omega, and phi are constant. This motion is called simple harmonic motion, or we can denote it by SHM, a term that means the periodic motion is a sinusoidal function of time. The quantity xm, I have already mentioned, is called the amplitude of the motion. That means the maximum displacement is a positive constant whose value depends on how the motion was started. The subscript m stands for maximum, because the amplitude is the magnitude of, I have already mentioned, maximum displacement of the particle in either direction from the origin. So one simple harmonic motion can be the displacement of the particle at any instantaneous time can be expressed by this equation. Okay, so this is an equation of simple harmonic motion, or this gives the displacement of any time. This represents the displacement of any time for a particle executing simple harmonic motion. Okay, so I have already explained this one. Suppose the particles, this is the 0 time. Particle starts from here. When it comes here, it is actually, this time is 1/4 of the period. When it comes here, half of the period, and it completes the period over here. Okay, So if you want to represent this displacement as a function of time, so it has got the maximum displacement, which we call it amplitude at 0 time, and 1/4 of the time it comes to its displacement is 0, and where it is again the amplitude is maximum at half time, 0 at 3/4, and then it is positive maximum when it completes the full oscillation. Okay. What about the period? In the first figure, we have seen that the so there's a displacement as a function of time. Okay. What about the speed? The speed is 0 actually here. Speed is 0 here, and speed is maximum here, and also speed is maximum over there. Okay. So speed is greatest at x equal to 0, and speed is 0 at the extreme position, means here, there, and there. At extreme position, that means at the position of the maximum amplitude, maximum displacement, that means in amplitude, its velocity is 0. Okay, so we have already explained about xm. Another thing, now the time varying quantity omega t plus phi is called the phase of the motion, and the constant phi is called the phase angle. Phase constant, phase angle, or sometimes it's called epoch. The value of phi depends on the displacement and the velocity of the particle at time t equal to 0. To interpret the constant omega, which is called the angular frequency of the motion, we first note that the displacement xt must return to its initial value after one period t of the motion. That is, xt must be equal to xt plus t after completing one full period, full oscillations for all t. So that means, so in the equation number 2, we put at first t equal to 0. So that will be the result. And when t equal to t plus t, that's the result. Okay, so these two must be equal. So from here, xm, so these two will be equal when it fulfills this condition, omega t plus t. So that must be equal to omega t plus twice pi. We know that cos of omega t must be equal to cos of omega t plus twice pi, because after twice pi, it completes the full oscillation. So that means omega t cancel out. So omega t must be equal to twice pi. So omega will be twice pi by t, or it will be twice pi f. So as you see, the SI unit of angular frequency is actually per second, or we call it radian per second. Okay. So in this figure A, we draw two simple harmonic motions having different amplitude, but their frequencies or the time period are same. So sometimes we ask you to draw two simple harmonic motion having same period and frequency but different amplitude. Look, why it is different amplitude? Because it starts from different positions. Okay, however, it becomes 0 at the, and this is the 1/4 of the period, half of the period, 1/4 of the period, and complete half of the period, 3/4 of the period, and complete period over here, and so on. And this figure shows two simple harmonic motion having now look at the amplitudes are same. However, the time period for this one, the purple one, that's the complete time period. And for the blue one, that's the time period. That means time period is for one time for the blue one, time period is double of the purple one. Okay, so the amplitudes are same in this case, but frequency or time periods are different. Actually, time periods are double of the other one. And this figure shows the two simple harmonic motion having same frequency. Look at the same frequency and period. When it will have same frequency, it will have same period. However, the phase angles are different here. Okay. Okay. So now another this curve actually represents. If we can come later here, like so, you know the x is actually xm cos of omega t plus phi. So to find out the velocity of this, velocity of the particle executing simple harmonic motion, we should differentiate the displacement with t, with respect to t. So d dt of xt will be this one, which is minus omega xm sine of omega t plus phi. So if you plot this equation, this velocity as a function of time, so this is the displacement as a function of time. We have already explained this one. When you draw the velocity as a function of time, the curve will be this one. When at t equal to 0, so sine term will be 0, so velocity will be 0, which is shown here. Velocity is 0. Okay, and other thing. And to find out the acceleration, we will differentiate velocity again with respect to time. Okay, with respect to time. And if we do that, we see that it will be another omega will come here and minus omega square xm cos omega. However, you see this term is actually x. This is x. That means if we differentiate it again, so it will get acceleration, and acceleration is actually minus omega square times the displacement. So that's the beauty of the simple harmonic motion. So that means the motion repeats itself again. So that means in simple harmonic motion, this is the one of the criteria or important property of the simple harmonic motion is the acceleration is proportional to the displacement. Acceleration will be proportional to the displacement, but opposite in sign. And the two quantities are related by the square of the angular frequency. And if you plot acceleration as a function of time, look, it will be similar to that one, except at the negative sign, opposite to that one. However, the shape of the curve is exactly same as the displacement. So it started from positive xm, and it will start from negative xm multiplied by minus omega square. That would be the exact value. Okay, so we have seen that acceleration is, so any motion for which the displacement is, acceleration is proportional to displacement, we call it simple harmonic motion. Now the fourth law of simple motion. So we know that the acceleration of the particle of simple harmonic varies with time, and we can use Newton's second law to learn what force must act on the particle to give that acceleration. So F will be m times the acceleration. Substitute the value of acceleration for the particle executing simple harmonic motion, which is minus m omega square, so it will be minus m omega square x. You see the m and omega will be the constant for a particle executing simple harmonic motion. Okay, so we can write instead of m omega square as k, where k is called the force constant or restoring force. So F will be minus kx. And for spring, k is nothing but the spring constant. Okay. I don't know, in your physics lab, you might have done an experiment with a spring. Okay. So there will be a spring, and then you will hang some mass at the end of the spring, and then if you when it starts to move, so that motion will be simple harmonic motion, and using that simple harmonic motion, you can determine the spring constant of a spring. So k equal to m omega square, and from here you can find out omega. Actually, omega will be square root of k by m. Yeah. So you can in fact take equation 7 as an alternative definition of the simple harmonic motion. It says simple harmonic motion is the motion executed by a particle subject to a force that is proportional to the displacement of the particle but opposite in sign. Okay, so now the mass spring system. So in this system, when mass M is attached to a spring, okay, and other end of the spring is tied here, okay. So this mass spring forms a linear simple harmonic oscillator, or we can in short we can call it linear oscillator, where linear indicates that F is proportional to X rather than some other power of X. The angular frequency omega of the simple harmonic motion of the block, as I showed you from the equation number 7, omega equal to root over k by m. So if this is the omega, you can calculate the period t. T will be twice pi divided by t is actually, we have derived this equation earlier, t equal to twice pi divided by omega. And if you substitute the value omega in the denominator, so this will be just rotate. Numerator will be the denominator, denominator will be the numerator. So t will be twice pi root over m by k. So from here we can calculate the time period for this linear oscillator. So equation 8 and 9 tells us that if the object is large, tells us that a large angular frequency and there's a small period. When the angular frequency is large, period will be small, goes with a stiff spring and a light block. So for that one, for smaller time period, M has to be small, K has to be large. Okay, that is what it said. So K is large when the spring is very stiff. Okay. Every oscillating system, be it a diving board, you know, in a swimming pool, there's a board, okay, so from where you can dive. So diving board, or when you play a violin or guitar, the violin string has some element of springiness. That is why, so when you distort that one, it comes back to its original position. So it has some sort of springiness and also some element of inertia or mass, and thus resembles a linear oscillator. The springiness is entirely in the spring, which we assume to be massless, and the inertia is entirely on the block, which is assumed to be rigid. Okay, so now what is the energy of the simple harmonic motions? The energy of the linear oscillator transfer back and forth, I showed in the first figure. When it is moving back and forth, actually it converts energy from potential energy to kinetic energy, and kinetic energy, potential energy, and so on. Okay. And if the system is isolated from the environment, then it will move forever. Okay. If there is no dissipation of energy. And you can form this sort of oscillator in using inductor and as an electrical engineer, in an inductor and a capacitor. When you make an LC circuit, so in that case, energy will be converted from electric energy to magnetic energy. Electric energy, magnetic energy. But in this case, energy is converted to potential energy to kinetic energy, potential energy to kinetic energy, and so on. Okay. So the total energy, when the oscillator transfer back and forth between kinetic energy and potential energy, and sum of these two energies is called the mechanical energy, E of the oscillator. So when it is moving back and forth, total energy actually remain constant. It is independent of the displacement, position of the oscillating particle. We are going to prove that one. We now consider this situation quantitatively. So potential energy of a linear oscillator, that means the mass spring system, is we can write that this one is half of kx square. And so if we write at half of kx square, and the x is actually xm cos omega t plus phi, so it will be half of k xm square cos square omega t plus phi. The kinetic energy of the mass spring system entirely with the block, its value depends on how fast the block is moving. So it depends on the velocity of the moving or oscillating particle. So kt will be half of mb square. We have already derived an expression for the b using x, and that was minus omega xm. So b square means omega square xm square sine square omega t plus phi. So this is the potential energy, and this is the expression for kinetic energy. And if we substitute omega square as k by m, so this equation will become half of k xm square sine square omega t. Okay, this is, instead of omega square, you will put k by m. Okay, so mm cancelled out, so it will be half of k xm square sine square omega t. Now, if you add this 10 and 11, half k x square is common. So you have sine square omega t plus phi plus cos square omega t plus phi. So then we know that sine square theta plus cos square theta equal to 1. So finally, it will be u is equal to u plus k. So that will become, as I said, half of k xm square cos square theta plus sin square theta. It's like that, okay? And this term is actually 1. So it will be half of k xm square. Or you can write half of k is actually m omega square x m square as well, okay? You can write that. So that means, look at here, so m is constant, omega is constant, and xm is the maximum, that is also constant. That means total energy E remains constant. There is no, it is not function of x, function of t. So total energy remain constant. So we can state that the mechanical energy of a linear oscillator is indeed constant, and it is independent of time and also independent of position. So in this figure, if you plot energy, all energy, potential energy, kinetic energy, and the total energy or mechanical energy as a function of position, you can see that I have already explained in the very beginning. When you are at xm, positive maximum position, so it has got kinetic energy is 0 because velocity is 0, so kinetic energy is 0. However, it has got maximum potential energy. When it started to move, its potential energy is, and then as soon as it moves, it will have both potential energy and also kinetic energy. And over here, kinetic energy potential energy is same. So 50% will be the potential energy and 50% energy will be the kinetic energy. And when it moves here, the potential energy becomes 0. And then total energy, so full energy will be, full potential energy will be converted to the kinetic energy. And then kinetic energy will be decreased, and over here, potential and kinetic energy will be same. And then here, the kinetic energy will be 0 and all the energy will be the potential energy. Okay, and this black line, so every time when you add kinetic energy potential energy, so look here potential energy is maximum over here and kinetic is 0, so you are here. And in this case, potential energy is 0, kinetic is maximum, so you are here. And in this extreme case, potential energy is maximum, kinetic energy is 0, so total energy is here. So that means it is independent, or over here, kinetic and potential energy. So total energy will be again here, and over there, total energy will be there. So it is immaterial where the particle is, the total energy will always remain constant. That is independent of the position, independent of position. And from this figure, if you plot this, the purple one is the kinetic energy. Okay, so kinetic energy is 0 when you at t equal to 0. we are plotting energy as a function of time. In this graph, we plot energy as a function of x, and in this graph, we plot energy as a function of time. So that's the kinetic purple one is the kinetic energy. Kinetic energy is 0 at the beginning, and kinetic energy is maximum at t/4. So this is actually t/4, and again kinetic energy is 0 at half of the period, and then kinetic energy is 0 at the full period. And potential energy is the opposite one. Okay, potential energy is maximum over here. Potential energy is 0 over there. Potential energy is 0 over here as well. Okay. So again, if you add this kinetic and potential energy, this will be this black line. Okay, that's the sum. So this one is the kinetic energy, this one is the potential energy, and this black one is the mechanical energy. So again, from this graph, we can show that the mechanical energy is independent of time, and from this graph, we can show that the mechanical energy is independent of position. So we can make a statement: the mechanical energy of linear oscillator is indeed constant, and it is independent of time and also position. Okay, so now you see previously we have stated that the x equal to xm cos omega t plus omega t plus phi. Okay, now I have taken this one from another literature, another book. So in this previously we have chosen the particles oscillating along x-axis. Now in this equation we have chosen particle is oscillating in the y direction, and previously we have chosen maximum displacement as xm. Now we choose the maximum displacement as a, and previously it was cos function, and this is sine function. As you know that the cos function and sine functions all are periodic functions, so it is immaterial. Okay, so for a particle vibrating simple harmonically along y-axis, we can write y equal to a sine omega t plus alpha, which is actually similar to x equal to xm cos of omega t plus phi. So in this case, y is the displacement of the particle at any instant t, and a is the amplitude, and alpha is the phase angle or epoch that we have of the vibrating particle. And if we define, now we are going to derive the differential equation of a simple harmonic motion. Okay, so as this is the displacement of the vibrating particle. Okay, so if you differentiate this one, you will get this equation, and then if you differentiate it again, you will get this equation. Okay, and you know that the a sine omega t plus alpha equal to y, so d square y dt square b minus omega square y, and then if you take it in the bring it in the left hand side, so this will be 0. So this equation 3 is a differential equation of a simple harmonic motion. Okay, so in the exam sometime I ask you to derive the differential equation of the simple harmonic motion. This is the differential equation of simple harmonic motion. And what is the solution of this equation? So you have already learned the technique of finding out the solution of the differential equation, ordinary differential equation. Okay, and solution of this equation is this one. So here d square y dt square represents the acceleration of the particle, and previously equation 3 represents the differential equation of the simple harmonic motion. Already said that. It also shows that that in any phenomena where an equation is similar to the equation 3 is obtained, the body executes simple harmonic motion. So general solution of this equation is, already said that, y equal to sine omega plus. Also the time period of a vibrating particle can be calculated from equation 3. From equation 3, omega square will be this one divided by y. Okay, minus term will be of course there. So magnitude of omega d square y dt square by this, and as you know that d square y dt square is actually the if y is the displacement dy dt is the velocity, d square y dt square is the acceleration. So you can write acceleration, and y is basically the displacement. So omega is actually x square root of acceleration divided by the displacement. You may need this formula for solving some problem. So and t equal to twice pi by omega. So substitute the value of omega. So this will be numerator will be the denominator, numerator will be the numerator. So it will be twice pi square root of displacement by accelerations. So in these two slides, we have derived a differential equation of the simple harmonic motion, and we have shown that angular frequency omega is square root of acceleration by displacement, or time period t is equal to twice pi square root of displacement by acceleration. Okay, so now we're going to find out the average kinetic energy of the vibrating particle, average kinetic energy. So displacement of a vibrating particle, as in the previous slide, y equal to a sine omega t plus alpha. So velocity of the particle will be v equal to dy dt is this one, and if m is the mass of the particle executing simple harmonic motion, the kinetic energy will be half of mv square. So substitute the value of v here, it will be this one. Now, how are you going to find out the average kinetic energy of the particle? Average kinetic energy is, this is the, if you draw this particle, if this is y direction, so it will be a sine at t. So as a function of t, curve will be like that. In this case, this curve will be this one. Okay. So your task is to find out the average kinetic energy. So when the particle is here, kinetic energy is 0. When the particle is there, kinetic energy is 0. When the particle is there, kinetic energy is 0. But when the particle is here, it has got kinetic energy and kinetic energy maximum over there, kinetic maximum over there. So you're going to find out the average kinetic energy. Now, what is the average kinetic energy? Average kinetic energy is you will add energy at every point, and this is the time total in this time. Why you have chosen this time? Because this is the time for a complete oscillation, so time period t. So normally when we find an average, so we add everything and divide it by the time. So in this case, so you will calculate, you will add, so we will complete the adding by integration, adding from 0, this is the 0 time, to the complete time t for the kinetic energy of the whole period of time. And to find out the average, you have to divide it by t. So that's the division by t. So that's the average kinetic energy of a particle executing simple harmonic motion. Okay. Now to solve this integration, you know how to solve it. What we are going to do, we will multiply here by so you have half of, so we will multiply it by 4. So if you multiply it by 4, we have to divide it by 4. When you multiply it by 4, it will be 2 cos square omega t plus alpha and divided by 2 here. Or look, cancel out, it become this one. Okay. Now what is 2 cos square omega t plus alpha? 2 cos square omega t plus alpha is 1 plus cos of twice omega t plus alpha. And then this will be integration of dt and integration of this one. This is the total integration of the total period. Okay. Now, as you know that whether it is sine function or cos function, like look, so integration means whatever the positive value you have here and whatever the negative value you have. So sum will be the 0. Sum will be 0. So integration of this part is 0. So you have integration of 0 to t dt. So integration of t, so it will be just t. And this tt cancelled out. So it will be m omega s square omega square by 4. That is the right idea. So in this term, second part is 0. So kinetic energy m square by 4t into t, and that's the second part. So that's 0. And this is m s square omega. What is omega? Omega is twice pi f, or sometimes we denote it by n as well. So you can write f square, 4 pi square f square by this, or again, or you can write f square. Okay, pi square m s square f square, where m is the mass of the particle, a is the amplitude of the vibration, and f or n is the frequency of the vibration. Also, the average kinetic energy of a vibrating particle is actually directly proportional to the square of the amplitude. So we have seen that for the particle executing simple harmonic motion, average kinetic energy is square of the amplitude of the particle executing simple harmonic motion. Okay, and an angular form of simple harmonic oscillator. Previously, we have explained linear oscillator. Now we are gonna explain angular form of the simple harmonic oscillator. So in this case, you have a disc here. We have a disc here, and this disc is suspended. This disc is suspended with an wire, with the fixed or rigid support. Okay. When you twist this one little bit, suppose this is the equilibrium position. When you twist it little bit in the either position of the equilibrium position, then it will acquire some potential energy, and this potential energy will be converted. So it will move back and forth. Okay. So adjacent figure shows an angular version of the simple harmonic oscillator. The element of springiness or elasticity is associated with the twisting of the suspension, because it is rigid here, and when you twist it, it will acquire some potential energy, and this potential energy converted to kinetic energy, so it will move back and forth. It will move through and fro over here. So, twisting of a suspension wire, because when you twist it, some restoring force will be in the twisted wire. Okay. This device is called the torsion pendulum, with torsion referring to the twisting. If you rotate the disc by some angular displacement from its rest, that means from its equilibrium position at theta equal to 0, this position, and release it, it will oscillate about the position in angular simple harmonic motion. Rotating the disc through an angle in either direction introduce the restoring torque, and in this case, the time period tau will be proportional to the theta. Okay, so and this constant is called the torsion constant, and this is denoted by kappa, Greek letter kappa. Okay, so here kappa is a constant called the torsion constant that depends on the length, diameter, and material of the suspension wire. Okay, and equation 14 is the angular form of the Hooke's law. Previously, we have seen that in the linear oscillator, f was minus kx. That's for the linear oscillator. Okay, and k is constant, x is the linear displacement. Now, angular in angular case, force is analogous to the torque tau. So we can call it angular version of the Hooke's law. To obtain the period of an angular simple harmonic motion, we replace the spring constant k by kappa, kappa. So and mass by the moment of inertia. Okay, and we replace the m with its equivalent rotational inertia I. Okay, you have studied in your college level physics. When for a rotating particle, the force on the rotating particle is torque tau, and when it is an angular displacement, we denote it by theta, Okay, and in that case, instead of mass, we use rotational inertia I of the symbol. So our equation for the time period will become t equal to twice by root over I by k. Previously it was twice I by kappa. Previously, in case of linear oscillator, it was t equal to twice pi root over m by k. Now it is I by kappa. Okay, so today we are gonna stop here.
Assalamu alaikum, sir. Sir, 117.